Alright, so in the last few videos we talked a lot about minimums and maximums, extrema, things like that. So now we're going to start talking about critical points and how they relate to the extrema that we've been talking about. So definition here, a critical point, also called a critical value or sometimes called a critical number, same thing either way. A critical point of f of x is some number c such that either f prime to c is 0 or f prime to c does not exist, so D and E for short. So basically, just a critical point is some value of x, okay, it's a value of x, we plug it into the function, it's a value of x, where the derivative is 0 or undefined. Okay? And a note we have to make is that c, whatever this value of c is, it has to be in the domain of the function f. Okay? So f primed of c does not exist, that means c might not be in the domain of the derivative, but in order to be a critical point, just by definition, this value of c has to be in the domain of f of the original function. So we'll see a lot of examples soon and in the next few videos and all that. But for now, let's talk about how does this relate to mins and maxes. So if we come down here, we have this fun fact here that tells us, let's zoom out just a bit. So this tells us if f of x has a local extremum, which remember, local extremum, that means a min or a max, right? That means min or a max. If f of x has a local extremum at x equals c, then c is a critical point of f of x. So that's the relationship between these two. So basically, if you have a local min or a local max, then that point has to be a critical point. Okay, that value of x has to be a critical point. And remember, critical point, the definition we just talked about up here, is the derivative is 0 or the derivative does not exist at that point. Okay, so again, if you have a local min or a local max, then you also have a critical point there. So let's just see a graphical example of why that might be true. So this isn't really like a proof, but it's just sort of, it highlights most of the possible cases that we can have here. So example 1 here, let's zoom in a little bit on this graph. So we have this function y equals f of x, local min, local max, local min, local max, local min. So let's zoom in down here, look at the local min. So our fun fact tells us that because we have a local min here, then either the derivative at -4 has to be 0 or undefined. Okay, so let's think about this for a sec. So remember, derivative is the same thing as slope, right? Derivative of a function is the slope of the function, which is the same thing as the slope of the tangent line at that point. So if we want to draw a tangent line to this function at this point, what's it going to look like here? Well, if we try to draw a tangent line at this point, it's going to be a flat horizontal line, right? And remember, horizontal lines, they have slope 0. So this means that f primed of -4, is that's the x value here, that's our c right here, -4, it equals 0. Okay? So f primed of -4 equals 0 because the tangent line is horizontal, and horizontal lines have slope 0. Okay? So that just kind of verifies, or it's an example of the fun fact that we have down here. So let's come up to this local max here. So when x is -1, we have a local max, okay? And also, if we try to draw a tangent line here, we're going to end up with a flat horizontal line, okay? So that's, that means that f primed of -1 equals 0. Okay, because remember, the derivative evaluated at -1 gives you the slope of the tangent line at x equals -1. And the tangent line at x equals -1 is flat horizontal, which means the slope of the tangent line is 0, which means the derivative at -1 has to be 0. So f prime to -1 is 0 here, okay? Here, if we look at this local min, it's the exact same thing. So if we try to draw a tangent line here, it's going to be flat horizontal. Okay, so that means you know, the slope of the tangent line here is going to be 0 because it's just a horizontal line, and horizontal lines have slope 0. So the slope of the tangent line, that's the same thing as the derivative. So the derivative f prime to 2, f prime to 2 equals 0. Okay, because when x is 2, we have a horizontal tangent line, and the slope of a horizontal line is 0. So the derivative, remember, it's the same thing as the slope of the tangent line, so that means f prime to 2 is 0. Okay? So this one's going to be a little bit different. So local max, now we have a local max, so our fun fact from earlier down here tells us that we either have derivative equal to 0 when x is 4, so f prime to 4 is 0, or f prime to 4 does not exist. Well, if we look here, what happens here at x equals 4? We have a jump discontinuity, right? So if we come into 4 from the left, we go up here, but then immediately after that, we jump down here to this piece. So it's a jump discontinuity, and remember, if the function is discontinuous for any reason, then the derivative does not exist there. So actually f primed of 4 does not exist. Okay, f prime of 4 does not exist because the function is discontinuous at 4. So the derivative does not exist there. Okay? So that's also just an example of what the fun fact tells us. And then down here, here's a local min. Okay, so we have a local min, so that means we have to have a critical point here, right? And actually we do. So what is this? This is a sharp point, right? So this piece comes down like this and then just goes straight back up, kind of almost like a V, right? So there's a sharp point here. And remember, derivatives don't exist at sharp points. So we saw that several videos ago. Derivatives don't exist at sharp points. So f primed of 5, this is when x is 5, also does not exist. Okay? So f prime of 4 doesn't exist and f prime of 5 doesn't exist. And then for these guys, f prime of -1, f prime of 2, and f prime of -4, they're all 0. So this is just a graphical example showing the different cases that we can have with this, this fun fact here. So just to recap with it, if f of x has a local extrema, meaning a min or a max, at x equals c, then c is a critical point of f, meaning the derivative is 0 or the derivative is undefined. Okay? And we saw that up here. So we have a local min, which means we have to have a critical point, and in fact the derivative is 0 here. Here's a local max, which means it has to be a critical point, and the derivative is 0 there, as we can see. Here's a local min, so we have to have a critical point, and we do, the derivative is 0. Here's a local max, which means we have to have a critical point, and we do, the derivative is undefined. And same thing here, here's a local min, which means we have to have a critical point here, and we do, because the derivative doesn't exist. Okay? So it's really important to understand that, if you have a local min or a local max, then you automatically have a critical point. But it doesn't work the other way around. So in other words, if you know you have a critical point somewhere, that doesn't necessarily mean it's a min or a max. Okay? So in other words, you have to be careful about this. If x equals c is a critical point of f of x, then f of x may or may not have a local extremum at c. Okay? So this is what's called the converse. Here's a statement here. If f has a local extremum at x equals c, then c is a critical point of f. But it's not true the other way around. You can't go backwards and say, oh, well, if c is a critical point, then f has a local extremum. That's not true. Okay, that's the converse, and it's not true. So let's see a few examples of why this isn't really, or we'll see a few examples that illustrate the different possibilities with this. Okay, so we just saw here with example 1 that if we have a local min or local max, then we have to have derivative 0 or derivative undefined. Okay, so again, this wasn't really a proof, but it's just a picture that shows the different possibilities. So now we're going to see some examples that show the different possibilities with this. Okay, so let's make some room here. All right, so the first thing we're going to look at, it's going to be example 2. And our function is going to be f of x equals x squared. We'll come back up here. F of x, example 2. F of x equals x squared. All right, so this is example 2, part A. F of x equals x squared. So what's the derivative of this? The derivative f prime of x equals 2x, right? And when does 2x equal 0? Well, 2x equals 0 when x equals 0, right? So that means when x is 0, when x equals 0, f prime of x equals 0, right? So that's what we just solved this equation. 2x equals 0, so that means x equals 0. So in other words, when x is 0, f prime of x equals 0. So f of x has a critical point at x equals, or what we should say is f of x has a critical point x equals 0. So x equals 0 is a critical point of f of x. But is it a local min? Is it a local max? Is it neither? What is it? So if we draw a picture of f of x equals x squared, we know what that looks like, right? That's just a parabola. So x-axis, y-axis. Here's f of x equals x squared. Really bad picture, but it's got that general shape anyway. So let's zoom in a bit. When x equals 0, we're right here. And as we can see from the picture, it's a local min, right? It's a local min, okay? So here's an example of, okay, we have a critical point, and it's a local min. All right, so now that's example 2, part A, but let's do part B to see what's, what the difference is. So part B, let's say we have g of x equals negative x squared. So what's g prime of x? Well, it's negative 2x, all right? So when is this equal to 0? Well, let's set it equal to 0 and then solve. Well, if negative 2x equals 0, that means x equals 0. Okay, so in other words, just like before, when x equals 0, now we have g prime of x equals 0, right? So that's what we just found out here. So when x equals 0, okay, this is 0, g prime of x equals 0. Okay, so then that means by definition, okay, the derivative is 0 when x is 0. So by definition, so g of x has a critical point x equals 0. All right, but is it a local min? Is it a local max? Is it neither? Which one is it? Well, let's draw negative x squared and see what it looks like. Okay, so that's actually just the same thing as this parabola, but it's flipped upside down. So let's draw that. Here is negative x squared, f of x, or g of x equals negative x squared, x-axis, y-axis. And when x equals 0, let's zoom in just a bit. When x equals 0, we're right here. Okay, but we see it's a local max, right? So that's different from part A. So in part A, we know we had a critical point. Okay, in part A, we know we had a critical point, and it turned out to be a local min, all right? In part B, we know we had a critical point, but it turned out to be a local max, all right? So, everything's okay so far. Nothing fishy's really happening yet. But let's zoom out a bit, and let's look at part C. So part C is h of x equals x cubed. So h prime of x equals 3x squared. Now, let's zoom in a bit on that. So when does this equal 0? So let's set it equal to 0 and solve. So 3x squared equals 0. That happens when x is 0, right? So if we solve this equation, we just get x equals 0. So just like in part A and part B, that means that when x equals 0, h prime of x equals 0. Okay, so we just found out when x equals 0, h prime of x equals 0. So by definition, h of x has a critical point x equals 0. Okay, so now is it a min, is it a max, is it neither, which one is it? So let's separate this here, and let's draw a picture of h of x equals x cubed. So we're going to graph this x cubed function here. So if we do, we're going to have x-axis, y-axis. Now the function x cubed we know looks like this, right? Kind of sort of like that. Really bad picture again, but it's got that general shape. So this is h of x equals x cubed. Now when x is 0, we're right here, right? But notice this is neither a min nor a max, so this is not a local min, it's not a local max, it's neither. But the derivative is still 0 here, okay? So in other words, we have a critical point, but there's no min or max here, all right? So let's zoom out and look at all this here. So the point I want to make here is that, remember the fun fact that we had over here that we erased said, if you have a local min or a local max, then automatically right away it has to be a critical point. But it's not true the other way around. Just because you have a critical point, you don't necessarily have a min or a max. So here we have a critical point and it's a local min. Here we have a critical point and it's a local max. Here we have a critical point, but it's neither. Okay, it's neither a min nor a max. So just because you have a critical point, you can't automatically say you have a min or a max. So how can you tell whether it's a min or a max? Well, we'll talk about that in later videos. But for now, let's see another example. So these are all examples where the derivative is 0. Okay, what about the other, another type of critical point is when the derivative is undefined. So we'll look at examples like that, and then that'll be it for this video. So let's get rid of all this. But just to recap real quick, here's a critical point, but it's a local min. Here's a critical point, and it's a local max. Here's a critical point, but it's neither a min nor a max. So remember, just because you have a critical point doesn't mean you automatically have a min or a max. So you might have neither, like in the case with x cubed. So it is, But the other way around, so remember the fun fact said that if you have a local min or local max, then automatically you have a critical point. So you can say that much, but it just doesn't work the other way around. So let's look at example 3. So example 3, zoom in on this. Part A. So part A says f of x equals x to the 2/3. All right. So let's take the derivative. Okay, so we're going to find critical points. So f prime of x equals 2/3 x to the negative 1/3. So that's just power rule, right? That's just power rule. The exponent comes down as a factor like this, and then we subtract 1 from the exponent. So 2/3 minus 1 is negative 1/3. And then another way of writing this is 2 over 3 x to the 1/3. Okay. So to find critical points, we set the derivative equal to 0, or we find where the derivative doesn't exist. Now, this is actually never equal to 0. Okay, there's no value of x that's going to make this guy equal to 0. All right. However, if x is 0, then what? Well, if x is 0, then if we try to put that into the derivative, we have 2 over 3 times 0. Right? And we can't divide by 0, that's not allowed. So if x is 0, then the derivative is actually undefined. So if x equals 0, then f prime of x does not exist. Okay. So actually, by definition, that means, so f of x has a critical point, x equals 0. All right. So in all these examples we've done so far, the critical point was at x equals 0, but it's not always going to work out like that. I'm just trying to choose simple functions to show you the different possibilities that we can have. So anyway, also we want to point out that, remember, in order to be a critical point, the value has to be in the domain of the original function, and 0 is, right? So we can do 0 to the 2/3, that's okay. We can put 0 into f of x, but we can't put 0 into the derivative, okay? So the derivative doesn't exist at x equals 0. But the function does, so we do have a critical point. F of x has a critical point at x equals 0. So what is it? Is it a local min? Is it a local max? Is it neither? Which one is it? Well, if we graph this function x to the 2/3, let's come off to the side here and graph that. That's going to look like this. X-axis, y-axis. X to the 2/3 kind of sort of looks like this. X-axis, y-axis. So here, notice what we have here. At this, when x equals 0, we're right here, okay, and that's a cusp, C-U-S-P, cusp. So we talked a little bit about these in a previous video. But if we have a cusp, then that means the derivative doesn't exist, okay? So here, the derivative doesn't exist, but we see it's a local min, right? It's a local min, because even though the derivative doesn't exist, we can still talk about local mins, things like that. So it's a local min because it's smaller. The y value is smaller than all the ones around it. Okay, remember, that's just from definition of local min. So here we have a critical point where the derivative doesn't exist, but we have a local min, okay? So that's example 3, part A. So nothing really fishy with this yet, but let's take a look at part B. So we'll zoom out just a bit. Let's section off a piece over here. So for part B, let's take a look at g of x equals negative x to the 2/3. So, if you remember what happened in example 2, you'll probably guess what's going to happen here, but we'll just go through it. So g prime of x equals, just power rule again. Now we have a minus sign out front, negative 2/3 x to the negative 1/3, which is the same thing as negative 2 over 3x to the 1/3, okay? So actually, this is the exact same thing as part A, but we're just going to tack a minus sign out in front of it. Okay, we just tack this minus sign out front, but everything else is pretty much exactly the same. So, this is also never 0. Okay, g prime of x is never equal to 0, because there's no value of x that's going to make this guy equal 0. Okay, there's nothing that we can put in there that gives us 0 for this whole thing. But if x equals 0, then g prime of x does not exist. Okay, because if x is 0, then you have negative 2 over 3 times 0, and you can't divide by 0. Okay, that's never okay, never allowed. So if x is 0, then g prime of x does not exist. But x equals 0 is in the domain of the original function, so that means by definition, just like in part A, so by definition, g of x has a critical point, which I'll abbreviate. Oh, okay, we'll write it out. has a critical point x equals 0. All right, but you know, is it a local min? Is it a local max? Is it neither? So we can't say right away. Let's take a look at the graph and see. So if we were to graph that, you know, this minus sign, it's actually going to be the same graph as this, but this minus sign out front just flips it over the x-axis, right? So then what we have is kind of sort of something like this. Pretty bad picture, but it's got that general shape. All right, so again, we have another cusp here, right? This, I guess, is not really relevant, but what is this? Let's zoom in. Okay, so we have a cusp here. The derivative doesn't exist, as we've already seen, but it's a local max, right? So here's a local max right here. So part A, we had a critical point where the derivative doesn't exist, and it turned out to be a local min. Part B, we have a critical point where the derivative doesn't exist, and it turned out to be a local max, all right? So what about third possibility here? So let's zoom out. Let's see. So part C, let's say our function is h of x equals the square root of x. All right. So first of all, you know, we're going to want to take a derivative, right? Before we do that, let's write this as x to the 1/2. Okay, x to the 1/2. So h primed of x equals 1/2 x to the negative 1/2, just from power rule, right? That's just a power rule for derivatives. So, you know, another way to write this is 1 over 2 x to the 1/2, or 1 over 2 square root of x, but it doesn't really matter. So, just like part A and part B, this derivative is never equal to 0. There's no value of x that we can put in here that makes this whole expression equal to 0, okay? But just like in part A and part B again, if x equals 0, then h primed of x does not exist. Because if we let x be 0, then we have 1 over 2 times 0, and again, you can't divide by 0, that's not allowed. But 0 is in the domain of the original function h. So h of 0 is the square root of 0, which is 0, right? So 0 makes the derivative undefined, does not exist, but 0 is in the domain of the original function. So by definition, h of x, by definition, has a critical point. X equals 0. But is it a local min? Is it a local max? Is it neither? Which one is it? Well, let's graph the square root function here. So if we were to graph that, let's do that over here. X-axis, y-axis. So the square root function we know just kind of looks like that. Kind of, sort of. So when x is 0, we're right here. But what is that? Is that a local min? Is it a local max? Is it neither? It's actually neither. So remember, you might think it's a local min at first glance because it's smaller than everything else. But it doesn't satisfy the definition of a local min because, you know, you can't put a small interval around this, right? So remember, local mins and local maxes, they can't happen at endpoints. They can only happen in between. Okay, so we can't have a local min at this endpoint. So this 0, when x equals 0, that's an endpoint, and we can't have a local min there. So this is actually neither. Okay, this is neither a local min nor a local max. All right, so let's zoom out and summarize this. So here, for example 3, we had a critical point where the derivative doesn't exist, and it turned out to be a local min. Part B, critical point where the derivative doesn't exist, and it turned out to be a local max. Part C, critical point where the derivative doesn't exist, but it turned out to be neither a min nor a max. All right. And back in example 2, we had a critical point where the derivative was 0, turned out to be a local min. We also had a critical point where the derivative was 0, turned out to be a local max. And we also had a critical point where the derivative was 0, and it turned out to be neither. Okay, so that was back in example 2. So again, we'll just, one more time, the point I want to make here is that, remember the fun fact that we had over here told us, if you have a local min or a local max, then automatically right away you can say the derivative is 0 or undefined at that point. But it doesn't work the other way around. Okay, so just because the derivative is 0 or undefined somewhere, you know, that doesn't automatically mean you have a min or a max. Or like here, this is a min, that's a max, but this is neither, right? So you have to be careful with that. It just doesn't work the other way around. So we'll see a few more examples of things like this in the next few videos. And then soon we'll start talking about how to use critical points to find local mins, local maxes, and things like that. And that's it for this video.